Hey folks, so this video I want to talk a little bit about the performance of a chaining-based symbol table. So let's kind of add a structure here just so we know what we're talking about. We know basically there are going to be, this array inside, right, of length m, and inside that, right, all these different linked lists. So situations we might want to analyze are something like adding an element or searching for an element. So how much time will that take? And also recall, right, that there are n elements inside, right? So here it's like, well, these things, right, there's n of these, there's 3 of them, okay? So basically, right, we want to look at this from the standpoint of, well, we're going to assume basically, well, okay, it's not even an assumption. So, okay, let's back up for a second. So remember a few videos ago I talked about our assumption that our hash codes had basically a uniform distribution? That's what we're going to use right now. So via that assumption, right, with the assumption that the keys are evenly distributed, what that means is that each slot should have n over m elements in it. Because if they're evenly distributed, that means there's kind of an even chance they would have gone in any different position. So if I throw in 10, right, those 10 basically have an equal chance of going into each of those slots. And so I can basically just do a division. I'm basically just averaging them, right? So if I have that property of my hash code, right, of my hash function, then I'll have n over m in each of the slots, right? And that's what I get from that assumption. Now that's why I kind of backed up a second, because at first I was going to say, oh, that's our assumption here, but we're not really doing an assumption here. We're using the previous assumption, right? So if the previous assumption holds, then we know that the average number of elements is how many we can expect to find in each slot. All right, so we know that, right? We know that there's n over n elements in each slot. What do we know about, how much work it takes? And for here, what we're going to do is basically assume that our metric is maybe like number of comparisons, like how many nodes I need to look at and check their keys. So how much work do I need to do? So in terms of basically doing a search, well, it's like search a linked list, right? We have a linked list of length n over m, and there's basically a chance of, I could see it, early, I could see it late, I could see it in the middle. That stuff gives me a 1/2 factor, right? If I'm searching a list. So as a whole, right, I get basically this n over 2m, right? So this is my time to do a search, right? So the n over m comes from the number of elements I expect to see in each slot. 1/2 is because, by the time I get through half of it, right, I may have had a good chance basically of seeing, the element that I was looking for, okay? So the other one, of course, is insert here. And the insert is basically going to be n over m, because what happens is in an insert, you don't want to add duplicates. So you got to look through that entire thing and basically verify that key doesn't already exist on the index before you actually go and add it. So you're obligated to look at everything. So in that case, right, you basically get n over m as your actual performance runtime. So it's not bad, right? We are basically looking at linear time here, but it's not bad, right? We'll be able to do better though, right? So the hope is that when we go into kind of our next idea, which is going to be linear probing, then we're going to hit constant time, which then is clearly better than this. Now there are some advantages to doing a chaining approach, but those we'll maybe talk about them on exercise or homework. That'll be kind of for you guys to figure out. All right, so that about does it for our discussion of chaining-based hash tables. Hopefully by this point you have kind of an idea of how they work, right? Their concept, how to trace them, what the code looks like, right? And as well as some of their performance. So I will see you guys in the next video.